Sanjay.
Well, thanks for the introduction, Bastien, and thanks to the organizers for the invitation to speak at this online workshop. It's too bad that we couldn't make it to Novosibirsk this year, and we had a great time in Novosibirsk last year at the conference. So I'm going to talk about some joint work with Paul Melotti, who is finishing his postdoc in Fribourg, and who will move to Orsay next year, and with Paul Thévenin, who finished his PhD at École Polytechnique and is moving for postdoc at Uppsala next year. I'll first discuss some combinatorial results, then I will discuss some probabilistic results, and in a third part, I will give you some ingredients of the proofs. So I gave my first research talk 7 years ago at the University of Heriot-Watt in Edinburgh, and it was the probability seminar organized by Sergei Foss, and Sergei gave me a few advice on how to give a good talk. And one of them was that a good talk should be progressive. He said something like, the first sentence should be understandable by a small child, and the last sentence maybe by God. So I don't know about the last sentence, but my talk would be progressive, and normally the beginning should be understandable at primary school level. So beginning, if you have 2 points in the plane, A and B, you can draw the perpendicular bisector of these 2 points. It's the line of all the points that are at the same distance of the 2 points A and B. Now, if you have 3 points, A, B, and C, you can draw the perpendicular bisector of AB, AC, and BC, and you get 3 lines that intersect at a point, which is the center of the circle going through A, B, and C. So what we have here is 3 points and 3 lines that intersect at a common point. So these 3 lines, since they intersect at a common point, they define 6 regions in the plane, and each of these regions either contains one of the 3 points or does not contain any point. So we will call them the occupied regions or the empty regions. And it's easy to see that you cannot have 2 points in the same region, because whenever you have 2 points, they have to be separated by their perpendicular bisector. And so we want to characterize the configurations of points and lines that we can get in this fashion. So we will encode this configuration by a word. I call this an occupancy word. So I start by this region. It's occupied, so I put a 1. The next region is empty, so I put a 0. Occupied, occupied, empty, empty, 1, 1, 0, 0. So this configuration corresponds to this occupancy word. And I ask the question, if I take different triple of points A, B, and C, what are all the occupancy words that I can get? So the first remark is that the set of occupancy words, of realizable words, is stable on the cyclic shift and mirror image. What is cyclic shift? Is if I have a word like this word here, I can just shift everything to the right by 1 and take the last letter and put it first. Or I can also reverse the orientation of the word. And if I can realize this word, then I can realize the one with the cyclic shift by just rotating my points. And I can get the word which is mirror image by just flipping my configuration in the plane. So the question is, we are looking at words with 3 zeros and 3 ones, and we are looking at equivalence classes of such words up to cyclic shifts and reversal. And there are 3 such equivalence classes, which are depicted here. I took one representative of each class, and I'm asking which of these is realizable. And above each word, I wrote also a diagrammatic representation. So this just means empty, empty, occupied, 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 empty. The crosses here are just like symbolic representation. It's not the exact location of a point. When I want to depict the exact location of a point, it will be with a black dot, and the crosses will just be for diagrammatic representation. So this one, it's not hard to see that it's not possible to realize it, because if you look at this vertical line, every time you have a line, it's a bisector of 2 points, so there should be 1 point at least on each side of the line. So it's not possible to have all the points on just one side of that line. So this is not realizable. This on the right is realizable. I just showed you an example 2 slides ago. And the remaining question is, can you realize this configuration? Occupied, empty, occupied, empty, occupied, empty. And what we proved with Paul Melotti and Paul Thévenin is that this is not realizable, actually. Whenever you take 3 points in the plane, you always get this configuration up to cyclic shift or reversal. So I will comment on why we got to this problem, but so this is a very natural question to ask, and actually the proof, you can give it to a bright high school student. It's not very hard, so I would expect that somebody has already come across something like that before in the previous millennia, but we couldn't find anything. We looked for references in French or English on the web. We didn't find anything. So maybe if some of you know of some possible place for a reference in Russian, it would be very welcome. But yeah, we didn't find any earlier reference. So why did we look at this problem? The original motivation was some geometric realization of the star triangle transformation for the Ising model. And the question we had precisely was, we had 3 points A, B, and C, and we had 3 branches of hyperbolas. One branch was one was a branch of a hyperbola with foci A and B, one branch of hyperbola with foci B and C, and one branch of hyperbola with foci A and C, and these 3 branches were constrained to intersect at a common point. And so we were wondering, where were these 3 points with respect to these 3 branches? And the toy question somehow was to have these branches degenerate to a straight line, and that straight line is the perpendicular bisector of the 2 foci. So it's this question that we just asked. So now that we have this this result, which is very easy for 3 points, we can ask how to generalize it to more than 3 points. So here are 4 points. The first attempt is you just pick any pair of points. There are and choose 2 pair of points, and you draw all the perpendicular bisectors. So the number of lines you have is capital N equals little n choose 2. And the number of regions is very large, and capital N plus 1 choose 2 plus 1 regions. And it's a big mess to describe already the regions and where the points are. So this is the question which is too hard to answer. So maybe something easier, you just pick little n points and you draw the n-gon. Then you draw the perpendicular bisectors of the n sides. So you have little n lines, and little n plus 1 choose 2 plus 1 regions. But again, it's difficult to characterize the configurations of points and lines that you can have like this, because already it's not easy to describe the configuration of regions. When in the case of 3 points, you know, there were 6 regions which were ordered cyclically, but here there is no order between the regions. So once you notice this, you understand that somehow the most natural generalization is the following. So you pick n points on the circle, and you order them cyclically around the circle. And you draw the convex cyclic polygon, n-gon, which is associated to these endpoints, and you draw the corresponding n perpendicular bisectors. So because the polygon is cyclic, these bisectors all go through the center of the circle. So these n lines define 2 n regions. And then you ask, what is the position of the points with respect to the line? So what are the configurations of points and lines that you can realize with n points and n lines like this? So on this example, you know, you start reading here. You have occupied, empty, occupied, occupied, empty, occupied, empty, empty, occupied, empty. So you get this occupancy word. And the question, the general question is, can one characterize all the occupancy words that are realizable in this fashion? So the occupancy words, when you have n points, they have n ones and n zeros. So when you have a word of n ones and n zeros, if you want to know if it is realizable, this is what you should do. First, you should cut the word into 2 halves. The first half and the second half, these are both words with n letters, and you add these 2 words term by term. So you get a word with n letters, And the entries of this word, there are sums of zeros and ones, so there are 0, 1, or 2. This word is called the signature, this word on n letters. And we say that the signature is interlacing if once you erase the ones, you have a non-empty word, so you have at least a 0 or 2, and the zeros and the 2s alternate, meaning that between two consecutive 2s, you have 1, 0, and between two consecutive zeros, you have 1, 2. So what we showed with Paul Melotti and Paul Devenin is that if you have a word with n ones and n zeros, it is the occupancy word of some configuration of points and lines coming from perpendicular bisectors of a convex cyclic n-gon, if and only if the signature is interlacing. So let me just run this theorem on 3 examples to make it more concrete. So suppose I give you this word. If you remember, actually, this is the word that you saw 2 slides ago, so it will be realizable. You first cut the word into 2 halves. First half 1, 0, 1, 1, 0. Second half 1, 0, 0, 1, 0, and you add them term by term. So 1 plus 1, 2, 0 plus 0, 0, and so on. So you get 2, 0, 1, 2, 0 as a signature. Then in the signature, you erase all the letters 1. You get 2, 0, 2, 0. It's a non-empty word. There's at least a 0 or 2. And the 2s and the zeros interlace, alternate. Between two consecutive 2s, you have a 0, and between two consecutive zeros, you have a 2. So by the theorem, it means that the word is realizable. On the right here, I put a diagrammatic representation of this word, and you can actually see directly this phenomenon of interlacing on the diagrammatic representation. How do you do that? I'm going to color the different regions. The regions, they come in pairs of opposite regions. There's one region and there's a diametrically opposite region. And when the two regions in a pair both contain a point, like here, I will color them in green when they are both occupied. When the two regions in a pair are both empty, I will color them in red. And when in a pair of opposite regions, one is occupied and one is empty, then I don't color them. I call them the uncolored regions. And the fact that you have an interlacing signature just means that when you look at the colored regions, forgetting about the uncolored ones, green and red alternate. So this is exactly the same thing as on the word level, but I just wanted to introduce this notion of colors of regions, because we will come back to this notion of colors when we are looking at a probabilistic model. So second example is this word. Is it realizable or not? So if I cut it into 2 and I add the 2 halves, I get the signature 22100. And if I erase the ones from here, I get 2200, which is not interlacing, but because the 2s don't alternate and the zeros don't alternate. So the 2s and the zeros don't alternate. You have 2 consecutive 2s. So by the theorem, this word is not realizable. And last example, how about the word 1010101010? So ones and zeros alternating. It's not realizable because the signatures has only ones. So when you erase the ones, it's the empty word. So yeah, this is not realizable by the theorem. So you can ask for something a bit more general. You know, in the theorem we had, the points were arranged in cyclic order, and we were taking perpendicular bisector of P1 and P2, P2 and P3, P3 and P4, and so on. But we can ask something a bit more general. We can look at a non-convex polygon, like here, and take the perpendicular bisectors and ask what are the configurations of points and lines that are realizable. And this time you see on this example that this region here contains 2 points. So the occupancy words are not just with 0 and 1 entries. You can have also bigger entries. And in this case, we do not know how to characterize the realizable word. That's an open question. So as I said at the beginning, what is really important is not just the realizable words, but the equivalence classes of words up to cyclic shifts and reversal. So we call such an equivalence class a bracelet, and we want to count the number of realizable bracelets. So we fix n, the number of points, and we want to know how many realizable bracelets are there with n zeros and n ones, and we call this number Bn. When n equals 3, I showed you that there was only one realizable bracelet. So B3 equals 1. And we computed the first few values of the sequence Bn. It's in our paper. For example, B4 equals 5, B5 equals 9, I think. And we get a sequence which is not in the online encyclopedia of integer sequences. So we couldn't connect this to any previously known problem. So we don't have a formula, an exact formula for fixed n for Bn, but we have an asymptotic. Bn grows like a power of 3, like 3 to the power n. And there is a intuitive explanation for this. Sorry, is that when you have, for example, a red region, and you are exploring your regions one after the other, the next region cannot be red, so it has to be either green, or it has to be uncolored and occupied, or uncolored and empty. And you continue like that, you always have essentially 3 choices. So that's where this number 3, this entropy 3 comes from. Okay, so do you have any questions about these combinatorial results? If not, let's move to the probabilistic. Yes.
Quick question: is this something you published already? I remember you were working on.
Yes, yes,
yeah. Okay.
There is the archive reference at the end. If you, my slides are on my website.
Yeah.
If you want, you can click on the link I put in the chat, and the last slide has the reference to the archive.
Thank you, Sanjay. Thank you.
Welcome. So now we were 3 people who were trained as probabilists, and we were doing this combinatorial geometry. The natural question for us was, how can we introduce some probability in there? So the objects that we have are the realizable bracelets, and we want to sample a random realizable bracelet. And there are somehow 2 natural ways to do that. Because the realizable bracelets come from configurations of points, either you can sample a uniformly random configuration of points on the circle and look at the associated bracelet, or you can sample a uniformly random bracelet. So I'll first discuss the first model, which is that you fix n, at least 3, and you sample n IID uniformly random points on the circle. You order them in cyclic order, and you draw the corresponding perpendicular bisectors. Then you can ask, okay, you fix a realizable bracelet. Sorry, what is the probability that I achieve this given bracelet by this method? So the answer is that it's always a rational number, and if you are willing to compute very tedious integrals, you will end up computing the exact value for the bracelet you want, but it's very tedious. The simplest example somehow is when you take n points and you take this bracelet, which has first a 1, then a 0, then n minus 1 ones, followed by n minus 1 zeros. Then for this bracelet, the probability is this very simple formula, n divided by 3 times some power of 2. But if you take more general bracelets, it becomes a bit horrible, these rational numbers. So this is for the probability of an individual bracelet. Then you can start to ask about some more global observables, some more aggregate statistics. For example, you can ask, how many regions of each color do you have? So I denote by Hg the number of green regions that you have, Hr the number of red regions, and Hu the number of uncolored regions. Actually, these 3 random variables are redundant, because in a realizable word, you know that green and red alternate. So the number of red equals the number of green. And you also know that the total number of regions is 2n. So this gives you the number of uncolored regions as a function of the number of green regions. So I just need to tell you, we just need to understand the distribution of the number of green regions. And we managed to compute the expectation of the number of green regions for fixed n. And it's this relatively simple formula, n over 2 times 1 plus 1 over 3 to the power n minus 2. So as n goes to infinity, there will be n over 2 green regions. There will be a total of 2n regions. So 1/4 will be green, 1/4 will be red, and 1/2 will be uncolored. Then you can ask also about the size of each region, because you will see that actually the green regions are on average bigger than the red regions. So you denote by Fg the fraction of space covered by the green regions. What does it mean? For each green region, you look at its angle, you sum all the angles of all the green regions, and you divide by 2 pi, which is the total angle around the circle, to renormalize, so that you have some fraction of space. Same for the fraction of red and fraction of uncolored. So the 3 fractions add up to 1. But this time you have just one relation between these 3 numbers. You don't have a second relation coming from interlacement. So I really need to give you at least 2 of these formulas. The third one is redundant, but you need at least 2 of them to know them all. And so here are the expectations of these fractions for fixed n. So again, for fixed n, you have a formula which is not too complicated. And you can take the asymptotic, and you see that for green regions, this is the dominant term divided by that. Asymptotically, the green regions will occupy 3/8 of space. The red regions will occupy 1/8. And the uncolored regions will occupy half the space. And then you can look at the fraction of space covered by the empty regions. So what are the empty regions? All the red regions are empty, and half of the uncolored regions are empty. So by taking the previous formulas and summing them, you will get that the expectation of the fraction of space covered by empty regions is 3/8 times a corrective term, which is quite simple. So asymptotically, 3/8 of the space is covered by empty regions. So all these formulas, for the expectation of the number of green regions or the fraction of space covered by empty regions, they are very simple. And the asymptotic is also a very nice number, but we have somehow no simple heuristic explanation for that. We just compute very complicated integrals for many and many pages. We have different formulas that we add up, and they magically simplify to give these very simple numbers. So it would be interesting to find a proof that is simpler and that, for example, will explain where this term comes from. Like one explanation for this term, one for this term, and very simple proof. So yeah, we don't have this proof yet. Yes, so then asymptotically, we can do something else. We can show that the different colors are equidistributed asymptotically around the circle, which means, for example, that you won't have all the green and red clustering in one part of the circle and then all the rest uncolored, for example. This is not possible. This is a very unlikely event. You will have them distributed equally all around the circle. So this is true whether you consider the number of green regions and different colors of regions, or whether you consider the size. You won't have all the large regions clustering in one area of the circle and then all the smaller ones in the rest of the circle. So well, maybe I will skip the formalization of this because I have only 6 minutes left, I think. So just remember this statement, which is formalized here. And I'll go to the second model of a second probabilistic model, which is just that you fix n and you have a certain number of realizable bracelets, capital Bn. And among all these, you pick one uniformly at random. So this time, we do not have a result for the number of green regions for fixed n, but we have the result asymptotically. And we also have the asymptotic equidistribution. And in that case, actually, you have a different distribution because you have on average 1/6 asymptotically 1/6 of the regions that are green, 1/6 that are red, and 2/3 that are uncolored. And so in this case, we have not only the first term for the functional convergence, but we also have the fluctuations that are Brownian. So let me give you now some ingredients of the proof. So first thing is that so far I was depicting n points on the circle by n black dots. I am going to add for each white dot at the opposite position on the circle, I will add a white dot. So now you also have n white dots on the circle and n black dots. And for each dot, you will add an arrow pointing towards the closest point of the opposite color. And once you know the sequence of arrows around the circle, it will determine the sequence of colors of the regions. So let me explain this over an example. Suppose you have this configuration of points and lines. At the opposite position of each black dot, you add a white dot. Here a black dot, there the opposite white dot. Then you can attach an arrow to every dot. So this black dot here, which is the closest white dot to it. So there's one white dot here and one here. The closest one is this one. So the arrow will point in that direction. For this white dot, the closest black dot is this one. So it will point in that direction, and so on. And you can notice that if you color the regions, the green regions correspond to two arrows pointing towards each other. And the red regions, there will be no dots inside the red regions, but if you look at the two dots immediately outside the red region, they will point in the opposite direction. They will go away from each other. And the uncolored regions, they correspond to arrows, two consecutive arrows that go in the same direction. So this explains why you have this interlacement, because you have, for example, arrows that go clockwise, 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 then all of a sudden, an arrow that goes counterclockwise. So this will be a green region if they point towards each other. Then counterclockwise, 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 and then at some point clockwise. So they will point away from each other, so it will be red. So this explains why green and red need to alternate. And for the probabilistic model number 1, associated to uniformly random points, the kind of events that we will be considering are events like I want to have a black dot with arrow pointing counterclockwise, followed by a white dot with an arrow pointing clockwise, followed by a black dot with arrow pointing counterclockwise. This is this type of local events that we will look at, some local configuration of colored dots and arrows. And what we use explicitly to simplify the computations is the following. So first, notice that you can only look at the at one half of the circle, say the upper semicircle. Because if you know the position of all the black dots in this upper semicircle, and you know also the position of the white dots on this upper semicircle, you know the position of all the dots on the entire circle. And you can represent this upper semicircle by an interval using the map x goes to exponential of 2I pi x. So what you have is an interval with n IID uniform random dots, and the colors are, again, independent from the positions and IID. And what we want to do is to, when you have, say, a dot, a black dot, you want to be able to reconstruct the arrow of the dot by exploring the neighborhood of this dot. So we change a little bit the model. We allow the length of the interval to be random. And in exchange, we have that we can use exponential spacings, meaning that if I look at the next dot to the right of this dot, it will be at a distance which is an exponential variable of parameter 1. I put it in gray because I don't know the color yet. Then I flip a coin, probability 1/2 black or white, so this is black. So I continue because I want to get to the next white dot, so another distance which is exponential, and the color is white. And I do the same on the other side. And so from this exploration, I can say that this arrow will be pointing towards this white dot. So this is how we do the computations for model number 1. And this is my last slide. So how do we do for the model number 2? Model number 2, remember, it's that we were drawing uniformly at random a bracelet from all realizable bracelets. So actually, it's more or less equivalent to deal directly with the words, the realizable words. So we sample uniformly at random a uniform random word. It's not very different from sampling a uniformly random bracelet. And what we do is that we associate to each realizable word a walk in the lattice Z2. How do we do that? So say you have this realizable word, you cut it into 2 halves, and you write the first half on top of the second half. So now you have a word with n columns, and each column is of size 2. And you associate a walk to such a word with n columns. When you see a column 0, 1, you take a left step. When you see a column 1, 0, you take a right step. And when you see a column 0, 0, 1, 1, you take an up step. So here I read the word 1, 0, so you have a right step, followed by 1, 1, so it's up step, followed by 0, 1, so it's left, left, up, and right. So this map from the words, realizable words, to the walks is almost bijective. Why is that? Because if you know the walk, if you know you have a left step, then you know that it's a 0, 1 column in this word. If you know you have a right step, you know it's a 1, 0 column. And if you know it's an up step, you don't know whether it's this or that, but you know that the columns 0, 0 and 1, 1 were alternating because they correspond to the letters 0 and 2 in the signature. So you just need to know whether the first up step is 1, 1 or 0, 0, and then you can determine what the other up steps correspond to because of this alternation rule. So it's a 2-to-1 map from realizable words to a certain class of walks. And what are the walks that you get? It's walks that take either left, right, or up steps, and which have a positive even number of up steps. So the uniform measure on the realizable words translates to a random walk, which with probability 1/3 goes right, when probability 1/3 goes left, and probability 1/3 goes up. And you condition it on having a positive even number of up steps. So now that we have this walk representation, it's quite standard to have the convergence to a Brownian motion with drift. And the only technicality is to deal with this conditioning that you have a positive even number of steps. And this is the end of my talk. Here is the reference for the article. Thanks for your attention.